The universe goes from plasma to normal matter. Normal atoms, right? Atoms get their electrons, right? We have nuclei, but we don't have any electrons on there, right? And so now, when I say we can see the Big Bang, I was lying a little bit, okay? We can't look all the way back through this timeline, right? When we look back, back, and we see not this moment of creation. We can't see that, right? But we see this point right here. We see, and this is called the photon decoupling, right? We see the universe at the instant it let the photons go free. Yeah.
What does this say? Something atoms?
To normal atoms. It goes from plasma to normal atoms, right? And by the way, that's a long time. That's almost all of the time, isn't it? Yeah, that's like 13.3 something, 33 billion years or something like that. Isn't that right? If it's 13.7, right? So this is like almost all the time, but it's a log scale, so it doesn't look like that, right? Okay. Okay. Now, blah, blah, blah. Okay. Yay. Go team. Okay. Already talked about that, right? Okay. Now, in the last, and this really should say 0.37 billion years to present, million years to present, right? Okay. We talked about this, stretches the radiation, matter dominated, blah, blah, blah. Okay. Okay. 2 or 3 minutes after the Big Bang occurs, so when is that? Well, it's somewhere in here, right? Okay. We start to get fusion happening. Now, what is fusion? There's 2 nuclear reactions that produce power. Fission is what we do, and we've controlled that, right? Fission is we split things apart, and fusion is what we would like to do, right? Fusion releases way more energy, and it's combining things, okay? So 2 or 3 minutes after the Big Bang, fusion starts to happen, right? You've got all these, you've got neutrons and you've got protons, and they start to combine, but there's a little problem. The early universe can only create hydrogen, deuterium, tritium, helium, and maybe some lithium. And then you're like, what are all these guys? Well, deuterium is hydrogen with a neutron. Regular hydrogen just has a proton, right? And that's it. Proton and electron, it's hydrogen, right? This is a proton, a neutron, and an electron. This is a proton, 2 neutrons along for a ride, you know. There we have it, right? Okay. If you've ever heard of heavy water is where the hydrogen is deuterium. It reacts chemically the same way. It's just a different isotope, yes? Did we study isotopes in chemistry? A little bit? Okay. And then we can make helium, but we can't, maybe some lithium, but there's a little problem here, right? And I'll show you that problem in a second. But there's something called Big Bang nucleosynthesis theory that says that if we look at all these things, there are 4 different varieties of atoms, the nuclei that we could have created, right? 75% of those things, right, are hydrogen, and 1/4 of them are helium. So if you look anywhere in the galaxy, if you look anywhere in the universe, right, and you just look at what's there, if you look at just what's there, you should see about 3/4 of it being hydrogen, 25% be helium. And of course, we've done this, and that's what we see, right? So now you can have any theory you want, but it's got to predict the background radiation. It's got to, right, and it also has to predict the universal elemental abundance, right? But the question is, why? The 2 questions. Okay, if the Big Bang only created those elements, then where do things like carbon come from? What creates those?
Fusion.
Fusion reactions, not in the Big Bang though.
God, fusion of something.
Where else is fusion happening? It's happening right now. 8 light minutes from us right now. The sun is making, our sun's probably not making much carbon, right? But stars are making the heavy elements, right? They make the really heavy elements with supernovas, and they make things all the way up to iron. The supergiant ones make things all the way up to iron, okay? But the Big Bang, if you look away from stars, the Big Bang could only create those, and I'll show you why. Okay? Now, by the way, why do we know this? Does anybody know why we know this much about this? We have spent billions, hundreds and hundreds of billions of taxpayers' dollars understanding nuclear fusion reactions. We know them so well that we don't even need to test weapons anymore. We can do it with computers. That is why the United States is unilaterally, we need to ban all weapons testing. Yes? Because we don't need to do it anymore, right? Did we spend all that money? Did we spend all that money to know about the Big Bang, or were we just trying to kill Soviets? Yeah, we couldn't let them kill us first, right? You know, right? Okay. Now, let me just show you this. This is a chart of all the possible nuclei. Chemists use that chart because they don't give a rip whether they're talking about carbon-12 or carbon-14, right? Physicists use this chart because we want to know what's in the nucleus, because that's what we care about. We don't care so much about the electrons, right? Now, if you look at this, these numbers here that you see, the element that it is how many protons, right? So this is 1 proton, 2, 3, 4, 5, 6, right? Let's not look at that for a sec, right? But let's look at this number that comes before. That number that comes before, and you've got it on your notes too, right, is how many particles there are in the nucleus. Now, the second thing you need to know is that the ones that are white might exist briefly but are just unstable. So if you look at that, their half-life is very short. Unmeasurably short, right? So suffice it to say that those guys won't stick around very long. Now, it's the Big Bang. It's a crazy time. It's in here. There's all these particles running around, okay? If a proton's sitting here and a neutron runs in, well, you've got deuterium. That's stable. Isn't that stable? Isn't that H2? 2H? There you go. And if another proton or neutron happens to come around, well, it's a party. Yeah? Now you've got tritium. Yeah? That's fun. Okay? And then if you toss another proton in there, right, you could get, you can go to helium, you can go here, okay? Now, you've got 4. You've got an atomic mass of 4, yes? Where do you go next? Because you can only add 1 particle at a time. The likelihood that 2 is going to join your party at the same time is very small. So where do you go from 4? Look at 4. Is there a 5? Is there a stable 5 anywhere? We don't know why this is necessarily. You look on your table. Is there a single stable 5? No, there's no nucleus with 5 nucleons. Nucleons are protons and neutrons. There's not a single one, is there? It goes from 4 to 6, doesn't it? Yeah? 4 to 6. There's nothing stable in there. The 5s are not stable, right? So it's like you can get it. It's like jumping from, it's like, oh, I can do that. I can do that. I can do that. How many have I done? 3? I can do this. But now it's too far. I can't get to that next one. I can't get to 6. It's too far. Okay? The only way that some lithium could have been produced by the Big Bang is that maybe simultaneously a proton and a neutron approached at exactly the same time, and it made a stable atom. Right? Now, keep going. Let's say you make it across there. It's like Lord of the Rings when they're jumping at the end of the Fellowship of the Ring, right? And they're jumping across those things that are like falling, right? Okay. Let's suppose you make it that far. You made it that far. You get to 7, right? Is there a stable 8? Not a single stable 8. Yeah, so we know that maybe some lithium was made. There maybe some things made it across there. But the likelihood that any of these guys, however rare they are, right, would get made, and then one of those would actually do this is very small. Like, it's probability, right? If this is 1 in a billion chance, and that's 1 in a billion, then it's the chance that anybody would make it across both is 1 in a billion times a billion. 1 in a billion, right? Is like never, right? So this is why we're pretty sure that there's really only 4 species made. 3 of them are hydrogen, right? And 1 of them is helium, right? Okay. So that's really good evidence of the Big Bang as well, right? And then we can talk about the future of the universe, right? People talk about this, right? It's possible that this is the size of the universe. This is as time goes on, right? The universe is expanding, but gravity is slowing it down, yes? Right? Okay, so as it expands, maybe gravity is strong enough that it's going to pull it back together, yes? Right, so that's this scenario. Another scenario is that it's just going too fast. It's never going to, it'll slow down some, but it's going to eventually just fly apart and never come back, right? And then the other possibility here is that we actually have a critical velocity, that we're going to expand, and as we approach infinite size, we approach 0 velocity, right? Now, these things correspond to actually 3 curvatures of space that we talk about, right? So we talk about negative curvature, we talk about flat curvature and positive curvature. And here we're just talking about the density of it. If it's got enough mass, that it actually has enough mass to curve the universe in a positive way. And if it doesn't have enough mass, it's going to be negative curvature. And I'll show you this. This is going to wreck your mind. I'm very sorry about this, right? Okay. But if it's positive curvature, we can do Euclidean geometry, but it turns out funny. Okay. With Euclidean geometry, If we draw a circle